All right, so in this video, we're going to be talking about 7.2, confidence interval for the mean where the population standard deviation is known. So assumptions for finding a confidence interval for mean when the alpha is known. So remember the alpha is that 0.01 or the 0.05 and stuff like that. So here we go. So the samples are randomly selected. So these are the assumptions we're going to make. The sample size must be at least 30, or the population must be normally distributed. When, and this only needs to happen, the sample size is less than 30. So if it's 30 or more, we're good. We care less if it's normally distributed. But if it's less than 30, it needs to tell us it's normally distributed, or we need to figure it out ourselves. So even with these assumptions, keep in mind there will always be a chance that our alpha, that the confidence interval, may not include the true population mean. So again, we get to that point where we're 99, 95, 90% confident, but even still, the actual population mean did not fall in it. That's why we're never 100%. All right, so here is our formulas to start doing some actual calculations. So a formula for the confidence interval of a mean for specific alpha when the population standard deviation is known. So remember that alpha just represents, well, here, if I'm 90% confident, my alpha would be zero point 0.1. If I'm 95% confident, my alpha would be 0.05. If I'm 99% confident, my alpha would be 0.01. Therefore, my alpha divided by 2 would be 0.05, 0.025, and 0.005. With these, we found that these z-scores all had negative values. But then we learned in the last chapter that it's symmetrical, so it's really plus or minus these z-scores. So these are the things, if you can just remember, this is most likely what you're going to be dealing with. If it's not one of these threes and it's like a random one, like 96 or 88, you would just take 1. So to get this answer, you would do 1 minus 0.9, 1 minus 0.95, or 1 minus 0.99 to get this, and then divide, and then look this up on the Appendix A Table E. These are the three basic ones that really and truly you need to memorize. This is what you'll be seeing a lot. 90 is 1.65, 95 is 1.96, 99 is 2.58. Again, notice the larger my confidence level is, the larger my z-score is getting away from the mean to contain more values in my range. All right, so we've done a lot of talking in the last video, and then in this, let's get into our first example. So our first example here is the number of jobs. So a sociologist found that in a random sample of 50 retired men, the average number of jobs they had during their lifetime was 7.2. The population standard deviation is 2.1. So notice that out of 50, this was my average. So this would be the sample mean. This would be the sample. But then it does give you the population standard deviation of 2.1. So these are the facts that you need to know. All right. I think it gives you some space, but I'm going to try to keep it all up here, but you can, of course, put it in the space provided. So part A here says find the best point estimate of the population mean. So the best point estimate of the population mean would be the only thing that we know, which is the sample mean. So the best point for our population mean would be the same value as our sample mean. So when you're asked this on the homework with this information, what do you start with? You start with the sample mean. That's the only thing you know. That's the only thing you can go off of. And in part B, now we're going to find the 95% confidence interval of the mean of the number of jobs. So remember the formula, we saw it a while ago, but the formula is the sample mean minus the Z of the alpha divided by 2 times the population standard deviation divided by the square root of the sample size. So for a 95% confidence, I'm going to take 7.2. Actually, I think it's plus or minus right here because we do it twice. So plus, or I'll do minus right here. I'll do plus or minus. We'll split it up. And then 95 is one of those ones that you need to have memorized. A 95% confidence interval for a z-score is 1.96. And then you take that and you're going to multiply it by 2.1, divide it by the square root of 50. Notice here, I didn't care if it was normally distributed because the sample size was greater than 90. Or sorry, greater than 30. All right, so this is what I'm going to calculate. So I need to figure out what 7.2 minus 1.96 is. So let's do that. So let me switch over to my calculator real quick. So here's my calculator. Make sure y'all see it. All right. So I'm going to take that sample mean of 7.2. I'm going to do the minus part first. And then I think it was for 95, 1.96 times. I'm going to do a control divide to make it a fraction. It was 2.1 divided by the square root. So that's going to be control x squared of 50. So there is the left side of my 95% confidence interval. I just went up, highlighted it, hit enter to copy and paste, make it a plus sign. There's my right side. So if I switch back over here, so my confidence interval after what I just wrote, y'all have it. I'm not going to rewrite it. I now know that my sample or my interval mean is 6 points. Let's see, in the homework, I saw that they wanted you to go by 2 decimal places. So this will be 6.62. So you have, the population mean then will fall between 6.62 and 7.78. So given that our sample mean was 7.2, with a 95% confidence, I think the population mean would fall between 6.62 jobs and 7.78 jobs. All right. Again, it could not fall on that. I could be completely wrong. All right. So let's do it again with a 99% confidence. So again, that's going to be the sample mean. So that's going to be 7.2 plus or minus the 99% z-score. According to the table, it was 2.58 times the standard deviation of 2.1 divided by the square root of 50. So I'm going to plug it into my calculator again. Just an FYI, I'm going to scroll up and highlight the minus one, and I'm just going to go and change that z-score so I didn't have to type the entire thing. So that's going to be 2.58, and I get 6.43. I'll then go back, highlight it, change that to a plus, and I get 7.96. So with a 99% confidence interval, I think the population mean for retired men would have between 6.43 jobs and 7.97 jobs. So again, notice the larger that confidence got, the wider my interval got as well. All right. So part D, which is smaller? And again, in this situation, the 95% confidence is smaller because I have more room for error. Right? Meaning, really and truly, I guess I have less room for error. So we'll go with less room for error. If I'm 95% confident, I can squeeze that interval a little bit less. So I do have a less room for error. But then if I have a larger confidence interval, I need more room for error because again, it could fall outside that and I want to be pretty darn confident. All right. So there you go. So hopefully now that you've seen the definitions, you've seen the formulas, now you've seen it in action, that is pretty much all you got to do. Big thing, if you can memorize that table for 90, 95, and 99, that will save you a lot of time to have to go back to table E on Appendix A. We do have some situations where they want like a random percentage. It feels like an 88%, and we'll have to go through the whole process. Oh, I didn't even know they did it all for you. So there you go, right there, all spelled out for you. So you can kind of guide it with me, or you did it with me as well. However, whatever you need for that. All right, let's look at the second objective. We're going to determine the minimum sample size for finding a confidence interval for the mean. So there is a minimum sample size that you would need to be so confident. Remember, the larger the sample, the more confident you can be. So sample size. So the answer to the question, how large a sample is necessary to make an accurate estimate, is not simple because it depends of your margin of error. How large of an error are you willing to make? If it's a small error, you need a large sample. If it's a large error, you can have a small sample. So the population standard deviation and the confidence level. Right. So again, it's going to depend on your margin of error, your standard deviation. If you get a large variance, you're going to need a larger size. If you got small variance, maybe not so much. And then how large is that confidence error? Remember, the larger my confidence, the more error I can make. The smaller my confidence, the less error I can make. Because again, my interval becomes a little bit smaller. So again, this is the margin of error equation. So again, you have error. Again, it's going to equal that z-score of whatever that alpha divided by 2 was, times the population standard deviation, divided by the square root of n. And what they want us to do is let's solve for n. If we want to know how large a sample size is, let's solve for it. So that's what we're going to do. So first thing I'm going to do is I'm actually going to divide by this z alpha divided by 2. So that'll get me E divided by Z alpha divided by 2. I now get a population standard deviation divided by the square root of n. At this point, I need to get that n. So I tell you what, I'm now going to multiply both sides by the square root of n. This will get that n from the bottom there. And then I'm left over here. So I'm going to kind of come over here. So square root of n E. Can't write an E. Hold on. E over the z-score, which equals my sigma. Now, to get rid of this fraction, I'm actually going to multiply by its reciprocal. So z alpha divided by 2 over E. So that will cross out. But what I do to one side, I must always do to the other side. So this is where I'm at now. So the square root of n is equal to sigma times z alpha divided by 2 over E. And then after that, to get rid of a square root, I just square both sides. So there is my equation, as you can see here. So it's the z alpha divided by 2 times my sigma divided by my margin of error, all squared. Again, E is the margin of error here. Then we're going to round up to the next whole number since the sample space must be a whole number. So if you get like 10 or let's do 111.3 or something like that, that would be 112. You can have part of a person, but you do need that part of a person to give you a good sample size. So always round up. All right, so let's determine our sample size in example 2. Talking about undergraduates' GPAs. So how large a sample is necessary to estimate the mean GPA of each undergraduate class at a large university within 0.25, so that's your margin of error here, and at the 99% confidence interval. That means your alpha or your z-score for 99 was 2.58. So this is your z-score and the population standard deviation of sigma. Once you know exactly what you're looking for, you can then plug it in. So you can see here, E is the 0.25, the sigma is 1.2. Again, this is part of our table that we're going to memorize is 2.58. They plugged it in. They got 153.3. Now, with rounding, you would typically round down because the 3. But because we need this part of a person, you're going to always round up. So it's going to be 154. All right. So again, a sample of 154 students is necessary to estimate the mean GPA of each undergraduate class at the university within a 0.25 error at a 99% confidence. So I would need to, again, survey 154 students to be able to do that. Again, note using technology, you can use more decimal places than specified in rounding rules or shown in the examples. However, we use the table E Appendix A. All right, I think that actually concludes that 7.2. Yes, it does. All right, so if you need more examples or more guidance, please reach out. I don't mind to keep helping. Other than that, I'll see you in the next video.